Last time we started discussing things like electric potential energy, right? We talked about, hey, remember how gravity had a force, but then it also had a potential energy associated with it because it's a conservative force, right? Which just generally means that it's not path dependent. I know the force from gravity only depends on distance away from these two quantities, mass 1, mass 2. And between those two, I could have this energy term that could go into different places, and that was essentially just work waiting to be done because of the force, right? And then we started comparing the electric force in the exact same way. We basically said, hey, look how similar gravitational force is to electric force. Wouldn't it make sense then that the potential energy looks exactly the same as it had in gravity? And we talked about all that. We went through how it can be now positive or negative because charge can be positive or negative. So, first things first, let's do a little bit of a review, a quick concept question on just what we were talking about last time. I have two positive charges of equal magnitude inside a paralleloplate capacitor like this. Don't worry too much about the potential energy between those two charges. Think about the potential energy inside, how it relates to the capacitor. Which particle has more electric potential energy? And sorry if it sounds like my voice is a little bit weird. I no longer have any sinuses to help my voice resonate. It's all just solid cement at this point. So I know I start to sound kind of weird and a little bit nasally, but it's allergy season never seems to end. So I see a couple guesses here, but charge A is the correct answer, but let's think about this. So we had a potential energy equation where we could describe it U is equal to K, Q1, Q2 over R. That's fantastic, but it's specifically for point charges, right? It's not actually something that we're going to consider here. We had another equation for when we're thinking about stuff like a uniform electric field. In that way, we could think about it more like we had when we were discussing work the first time, right? Remember that work is equal to a force times a distance. And work is essentially, potential energy rather, is essentially work waiting to be done. If I'm thinking about, let me find some sort of object. Here's a mug that I've got. It's got a certain amount of potential energy right now, right? Of course, it's some height above the edge of my desk. And that height tells me about, essentially, there's going to be a force pulling this thing down. The force times the distance it would fall. Would the work be done if it was released? That's the potential energy. If I raise it up higher, now it still has potential energy, but it has more potential energy because it has a larger distance to fall. So when I'm thinking about what's going on in this picture right here, let's compare how far does each particle have to fall. Particle B wants to go towards that negative plate. It's going to go that distance right there. Whereas particle A is going to fall all of this distance. It's going to feel the same amount of force because the electric field is uniform. But because it has a much greater distance to fall, that S is larger, the work to be done is larger, the potential energy of particle A is larger. So, before I read a bunch of stuff on this slide, I want you to think about this. Do you remember when we were first talking about electric fields? We started the discussion on Coulomb's law, which described the electric force, but then we said, hey, what if you took away charge number 2? Right? The electric field was how we could discuss how a particle would interact with any other charge surrounding it, not just this one in particular, not just Q2, but any charge that I could put in there. My electric field tells me how Q1 interacts with it. And we did that by essentially dividing by one of the Q's and saying, hey, that's the electric field and that's what's left. Electric potential is to potential energy what the electric field was to force. It's essentially taking that potential energy and removing one of the Q's. It's not the same as potential energy. There is a difference, right? I know they're very, very similar terms. We have potential energy on one side, U. Potential is V. And that's essentially telling us how would charges, react to being in this particular space. Right? What kind of potential energy would they have? Where would they tend to go? Let me word that sentence with the right emphasis here. Where would those charges tend to go? Where would they fall if there was a charge there? That's what potential is telling us. And at first, this might seem kind of like, why would we talk about this? We didn't consider it when we were talking about gravity. Where would potential even show up in the first place? Well, I want you to think about it like this. Think about how many times you have heard the term voltage or volt, right? Your wall sockets have typically in America 120 volts. In a lot of other parts of the world, 220 volts. A AA battery is 1.5 volts. A 9-volt battery has, unsurprisingly, 9 volts, right? Voltage is going to show up in a couple different places. This is how we're going to define it at first, but we're going to find that there's a few different uses for knowing this term, but the easiest way to describe it right now is to consider it as kind of a parallel to potential energy, just dividing by one of those charges. And that's why I've got this kind of dotted line around my charge Q right here, because imagine what the potential energy of that charge would be. Now pluck away that charge. There's still a potential there, even if there's not a potential energy anymore. And so we can define it just like that. We can say, hey, the potential is the potential energy of a certain charge divided by that quantity of the charge. And the units for that are going to be, it's essentially energy divided by coulombs, right? So joules per coulomb, or our unit, the volt. So keep in mind that this might be a little bit strange because the unit is capital V and the variable is capital V. So you could have a potential of 5 volts, right? Keep track of which one's the unit, which one's the variable, because that can get quite confusing quite fast. But it is a scalar, right? It's kind of like the electric field in that it is technically everywhere in space, but it's only a scalar value. It doesn't have any sort of direction associated with it. There's no little vector sign on top of that thing to make that, direction dependent. So let's try this out. Let's say I've got an electron and I'm going to accelerate it through a 1000 volt potential difference. Now, there's a lot of detail that's technically missing in this problem. We don't know anything about direction or anything else like that, but I'm not worried about it. I'm only interested in speed, right? So directionless kind of terms here. But let's go ahead and spend a little bit of time working on this one, and let's see what we get. All right, let's start to take a look at this one. So there's a lot of detail that I don't actually have here, right? There's a lot of things in here that I just simply don't know what direction this might be. Is the potential difference up, down, left, right? What's going on there? I don't know. But for finding the speed, it's not actually going to matter for us. Let's draw this thing out. So here's my electron, for example, a little tiny green ball. And we're going to talk about these in just a little bit. But let's say the potential is 0 volts right here and 1000 volts right here, right? That's 1000 volt potential difference. I'm going to pass my electron right through this potential difference. It is going to pick up, essentially, well, it starts with a bunch of potential energy, and it's going to end with a bunch of kinetic energy, right? That's how this transfer is going to go. So I could say, okay, well, how much potential energy does it start with? Well, I could rearrange my equation of potential is equal to U divided by the charge. Let's rearrange this to say potential energy is equal to potential times charge. And here's where a fun unit comes into play. We have volts. We have an electron. The potential energy could be written as 1000, and I'm going to do this in a different color because I think it's a little bit confusing at first, electron volts. Which sounds like I'm just smashing some words together, but I know it's been a little while. I think we've used this unit only a couple times now, but there is a special unit of energy called the electron volt, and it's quite literally the potential energy of an electron passing through 1 volt of potential difference. So if we've got 1000 volts and 1 electron, it's 1000 electron volts. And it's a little bit on the nose for a kind of energy term. Let me name it out first. So electron volt, unit of energy. This is actually a really useful value, though, because let's do a conversion real quick. How many electron volts, or what is 1 electron volt into joules? 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. It's kind of small, right? But when you're thinking about the energy of electrons and of particles, and I'm talking fundamental particles here, not just, the big ones like dust particles. In a case like this, having every single number as like 10 to the negative 15th joules every time is really kind of annoying, honestly. It's obnoxious, they're tiny, decimals everywhere, extra terms everywhere. It's kind of bothersome. So one of the common units that we actually use when we're talking about energies on a subatomic scale is the electron volt, because it's right around that subatomic scale, right? This charge of the electron is a very common charge in a lot of particles. So electrons, muons, tauons, protons, positrons, all sorts of particles have this fundamental charge E. So this is a very useful unit of energy to have for a lot of those types of experiments. And on top of that, if you're accelerating a bunch of particles, if you're accelerating a proton or an electron, how many volts do you need to get it up to a certain amount of energy, right? It just kind of, everything falls into place with this unit. So it's a useful thing to have. It is crazy small though, yes. But let's go ahead and use this. So we say, okay, well, we've got 1,000 electron volts, which if we do this conversion, there goes my draw pad. It's a good run while it lasted. So 1,000 electron volts would just be 1.6 times 10 to the negative 16th joules. Now, we know that all of this potential energy is being converted into kinetic energy, so U is equal to 1/2 mv squared. The mass of the electron, of course, is the same as it has been, 9.11 times 10 to the negative 31st kilograms. Rearrange this thing. 2u over the mass of the electron, square root, is equal to the velocity, which we should be finding something like 1.87 times 10 to the 7th meters per second, which falls into the threshold lickety-split. However, if you're looking for this on Canvas, I have changed the units ever so slightly because this is a pretty large number. So instead, I've put it into kilometers per second. So that's 18,700 kilometers per second. Pretty fast. But it's part of how we actually, not all of, but part of how we actually use particle accelerators. You get potential differences, and you run a bunch of particles through those potential differences. Because 1,000 volts is actually not, it's very high voltage, right? This is a voltage that will certainly kill you if you're not careful, but it's not super hard to create a voltage like that. In fact, if you're looking at the picture that we started with, if I remember right, this is a 20,000 volt switch that they open. So the potential difference between the two spots that the sparks are shooting out of is 20,000 volts, which is more than enough to create a plasma arc between the two. So it's what a lot of our power lines are running off of, right? It's a very high voltage, and then they scale it back down before they send it into your house, so your house doesn't, I don't know, explode with electricity. So, kind of just what we saw. The potential in a uniform field is probably one of the easiest cases that we can find to describe it, right? We saw last time that, and well, just in the problem from before, right? It's a work waiting to be done, E times Q times S. Here's what we've got for that potential. If we were to divide by the charge Q, we're left with just ES, right? That's all we've really got left. And this is a pretty simple case, but what that means is that the voltage is not constant throughout a parallel plate capacitor. A parallel plate capacitor has a uniform field, but the potential over here towards my positive charge is a very high potential. Over by my negative charge, I've got a low potential. Right? So the electric field does not necessarily, I can have one changing and the other not. And next time we're actually going to look at that relationship directly. But anytime I see a uniform field, I can always say, hey, the electric field would be the voltage difference divided by S. Right? So if I was to measure the difference between each plate, find the potential difference, divide by S, I would have the strength of the electric field, which we're not going to use right now very much. We'll have a couple places where we might, but when we actually go into talking about capacitors in circuits, you can use that to find the electric field inside a capacitor very easily, right? I would just hook up a capacitor to a 9-volt battery or something, and if I knew the spacing, I could immediately find the electric field. So there's some fun things to do with that. So what about a point charge, though? Right, that's a little bit different, but we can kind of treat it in the same way. Let's take that potential energy, divide by one of the Q's, so we're left with KQ1 over R, or just call it Q because it's the only one, and we get something that, well, it's kind of to be expected almost, right? It's a lot like the electric field, but it's over R instead of over R squared. And just in the same way, it couldn't be positive or negative, right? The potential could go either way on that one. But if we want to talk about this thing, there's a few different ways that we can actually take to describe it, if we would like. One of the easiest ways is going to be just some sort of potential graph, right? Have R as my x-axis, have voltage or potential as my y-axis, graph out the potential as it goes along. The equal potential and the contour map descriptions are very, very similar. One's kind of like a three-dimensional picture, the other's kind of like a cross-sectional picture, but they're trying to describe the same thing. They're kind of like how you would read a topography map. Think about when you're drawing a map or anything else, it's really almost impossible to accurately describe every single height change, right? Just think about what that picture would look like. It's incredibly hard to see. There's so much detail going on if you're trying to talk about every single little tiny difference in elevation at any point along a mountain. So instead what you do is you draw these dotted lines around an area, right? If I was trying to describe a mountaintop, then what I would say is I would do something like this. So here's one region and some dotted lines, and that's at a certain elevation, say 1,000 feet. Up a little bit more, I might see something like this. Now that dotted line is 2,000 feet. Now I might have something like this, where that's 3,000 feet. And I lose information about what's going on in between them. Right, there's a little bit of uncertainty about what's going on between those two dotted lines, but it gives me a very broad picture of what the shape of that mountain looks like. Just in the same way, if we take these contour maps, we're basically saying, hey, this is maybe 300 volts and 200 volts and 100 volts. And I lose a little bit of information, but I lose that information to simplify the picture so that it's much easier to see what's really going on. Right? Maybe we don't have the 100% clear picture, but we can make a lot of inferences about what's going on between those spaces at that point, right? The last way that we can describe these is kind of combining them all. It's making a three-dimensional graph, which works really great in MATLAB when you can like actually, move around and look at different angles of the picture. But when we're doing this in 2D, like on a slide or a piece of paper, it's a little bit harder to draw, a little bit harder to look at. It's not quite as clear. But it's kind of combining those ideas, right? It is just a three-dimensional graph, combining the ideas of the contour map with the potential graph. But knowing how to read these is going to be a very important point, right? Especially this contour map, we are going to use this a few different times. It's very useful for analyzing what a potential looks like. Speaking of, let's look at what a potential might be. So again, I'm losing some information here. I don't know what's going on in between. Oh, I'm using the eraser. I was confused for a second there. I don't know what's going on in here. I don't know what's going on in here. I don't know what's going on above here. I only see these dotted lines. Whoops. But in seeing those dotted lines, I've got a general sense. I can make some inferences about what's going on here, right? I can mostly assume it's a constantly changing potential. But let's say we put a proton right at this black dot. We've got plus 50 volts above, we've got negative 50 volts below, and we're sitting right on the zero potential line. That's where I put a proton. What's going to happen to this proton? What we've got here, I think E is most of what we're seeing, but let's talk about this. There's a couple different ways that I might imagine looking at this picture. Until we have a really solid idea of what's going on with the potential, right? Let me talk about three different ways that we might look at this thing. If this proton has a charge positive E, potential energy up here is greater than 0. Potential energy right here is 0. You might at first think, hey, potential energy where it's at right now is 0. It shouldn't move. But remember, potential energy is not its lowest at 0. Potential energy can become negative. Potential energy down here is less than 0. And if there's a lower potential energy somewhere, that's where the particle's going to want to go. Right? If it's at 0 right now, if you're at, I don't know, 0 elevation, but you see a lower spot down the hill, you're going to want to roll down the hill. Realistically, right? Who doesn't want to roll down the hill? It's fun. So that's what we might expect to see, right? And that's a very clean kind of exactly what we've been talking about with these equations way to think about this problem. Where the potential energies will be, it's higher up above, it's right in the middle where we're at right now, and it's lower down below. Which means if it's going to want to fall down there, we're going to see an increasing speed as it goes down. And this helps if you've got a good idea of how potential relates, or potential energy relates to forces, right? Remember, there's a derivative relationship between those two. Question. Let me talk about this in just a little bit. So I specified that it was a positive charge, but let's take a look at the second description and see how that might change. What would create a positive potential? Well, if we've just seen from this stuff, a positive potential would be created by positive charges. Let's imagine that there's some positive charge above us that's creating this positive potential. What creates a negative potential? Negative charges. Right? And again, we're kind of just pretending that they're there. They're not specified on the picture or anything else, but let me imagine for a little bit that a positive potential is created by those positive charges, a negative potential created by those negative charges. Where does the proton, a positively charged particle, want to go? Not towards the positive charges, certainly not. Right? And if I have it drawn out like this, as if it's a parallel plate capacitor, then I would expect a constant force pulling me downwards. That constant force pulling me downwards is a constant acceleration, but a non-constant speed, right? Acceleration means we're speeding up and up and up and up. So we would expect to be going downwards at an increasing speed because of those forces. The last thing I can do is kind of similar to this description, but we can imagine if, again, we have like the positive charges, the negative charges. One of the things that we're going to be looking at a little bit more next time is how do you find an electric field from a potential? And the electric field would be going from positive to negative. So we would expect that force to be going the same way as well. So my proton here would be moving downward at an increasing speed, but the electron would want to go up instead. Because for the electron, the potential energy is, and let me do this in a different color real quick, just so it's clear. When we're talking about something like the electron would actually be a negative E times the potential. So the lowest potential energy for the electron is up above. That charge does matter. We didn't consider it in this problem, remember, because we were only interested in speed. So I said the sign doesn't really matter in this problem, but if we're actually considering the direction, if we know what direction everything is going, then that negative sign becomes a little bit more important. So I'll erase that before we get too stuck on that one. Absolutely. Okay. So, just like we had talked about with potential energy, right? We have the potential energy between two particles. Sure, fantastic. What if we have more than two particles? Just like the electric field, just like the potential energy, all we have to do is sum up all of those potentials together. Right? If I'm looking at the potential at this point X, right in the middle of this ensemble of charges, I would take the potential from Q1 and Q2 and Q3 and Q4 and Q5, sum them all up together at that point, and I would have my total potential. Right? They just add up. There's no weird multiplication or anything else like that. Positive charges give us a positive potential. Negative charges give us a negative potential. And then there's that relationship again between potential and potential energy, which, don't forget, are two separate quantities. So, put it into practice. Here's a configuration that we've seen a couple times at this point, but what I want you to do is find what is the electric potential at that dot. So let's start taking a look at this. And I'm going to go ahead and steal this picture. I do see a number in chat that's looking pretty good. I like that one. Go ahead and write this out real quick. So we had, this was whiteboard. Oh no, 25 dash, how did I forget this already? 25-7 was that one. 25-7. Go ahead and paste our new picture in here for 25-8. And I'm going to go ahead and shrink this down just a little bit so it's a little bit easier to see all on the screen at once. So, as we were saying, when we have a bunch of different charges all contributing to potential, the only thing we really need to do is sum them all up together. So my total potential, let's go ahead and do some things to make this a little bit easier. I'm going to call this Q1, Q2, and Q3. And that's the order that I'm going to follow when I'm actually summing these things all up together. So I would have K times Q1 divided by, Q1 is now 0.05. It's 5 centimeters away, right? I've got a 3, 4, 5 triangle here. Which, again, Pythagorean theorem, you know what? I'm not going to parentheses that in. I'll make it a little bit easier to read, I think, if it's just 0.05. Pythagorean theorem will get you absolutely all the way there, but it's just a little shortcut. 3, 4, 5 triangles always have that relationship. I'm adding all of them up, and I would usually, even if they were negative charges, I would let them add up because the negative that I would plug into the Q would take care of that for me. But I'm just setting this thing up now. So KQ2 over thank you, 0.04. Now, you might remember last time I had like a little bit of a shortcut that I used to make calculations just a little bit easier for me to handle. And I'm going to use that one again. I'm going to take the fact that K is 8.99 times 10 to the positive 9th, nanocoulombs is 10 to the negative 9th, and I can cancel those details out, right? So this would become then 8.99 times, I have in the first one, Q1 is 4. The nanocoulombs have already been canceled out by the those values on K. So 4 over 0.05 plus 2 over 0.04 plus 2 over 0.04. And that's just, well, 0.03 is what I should have said. And that's just to try and make it a little bit easier, a little bit faster to calculate, less places for me to make mistakes. So plug in all of those values, we should find something like 1,768 volts. Just like that. Let's try another one. And before you dive into this problem all the way, I'm going to make a very heavy recommendation. Go ahead and copy this picture, and whatever you're working on right now, if it's like a tablet or anything else, go ahead and copy and paste this picture into what you're working on, your notes. If you're doing this on paper, go ahead and redraw this thing on there. Right, because we're going to use this for part C here. We want to draw some pictures, and I think it's a little bit easier if you've got 2 separate ones, ideally. It'll just make everything a little bit more clear. But anyways, I've got a positive charge at 1 centimeter. I've got a negative charge at -1 centimeters. Where, if anywhere, is the electric field 0? Where is the electric potential 0? And what do each of these look like if we were to sketch them out? So the question is, can we use potential energy here? Not necessarily. Because potential energy in this case, so you need 2 charges to do potential energy. Those 2 charges are the charges that are creating this electric field and potential field. I shouldn't say field quite in that same way, but you kind of get what I'm saying. It's going throughout all of space. Because we're looking for a spot somewhere around them, it might be directly on the spot, but not necessarily. You would want to be looking not at potential energy because, for example, if I was interested in knowing what's the potential right here, I'm still on eraser every single time. If I was interested in what's the potential energy right at that point, I wouldn't be able to find it because there's not a charge there. I could find the potential at that point, but not the potential energy, if that makes sense. Now, the other thing, remember, so the E is equal to Vs kind of works, but that equation is specific to when our electric field is uniform. right? It's only in a uniform electric field, and because I've got 2-point charges, there's nothing uniform about these ones. So that does give you a sense of how the electric field goes with the voltage, or the potential, I should say. We keep calling it potential, but in my mind, it's voltage. They're two words for the same thing, essentially. So I wouldn't necessarily go with that, but you can try to solve out for a point of where would that potential be 0. You can set it up algebraically, but you'd have to use the 2-point charge equations. All right, how's about we start taking a look at this? So again, I'll go ahead and I'm going to post 2 versions of this one in here, because again, I said it's a little bit easier if we can draw this thing out. So you know, let's go ahead and have 2 of these things. In the meantime, let's bring all these together so I don't have a bunch of different layers trying to interact with each other. Okay. So let me think about this thing conceptually for a little bit. I'm not going to try and set up too much algebra yet. If I want to think about the electric field coming from my positive point charge, my electric field on the right side would look like, whoa, that's purple. That's not orange. There we go. My electric field would look like that there. It would look like this in this region, and it would look like this over here. My negative charge would see an electric field going like this, an electric field going like this, and an electric field going like this. We did something similar when we first talked about the parallel plate capacitor, right? We took both of these things and we drew the electric field on all sides and tried to see how they would, you know, sum up together. So right in between these two, I can pretty definitively say, hey, both charges have an electric field pointing to the left. If there is going to be a region where the electric field is 0, it's certainly not going to be there. But then I look on the right and the left sides, and let's focus on the right for now, and I'll make the same argument for the left side after this. These are the same magnitude of charge. The orange charge, for any point that I could possibly pick out here, let me do that in not blue, so any possible point, any x that I could pick all the way out here, the orange charge is always going to be a little bit closer than the blue charge is. The electric field magnitude from the orange charge is always going to be a little bit greater than the blue charge. The field is always going to be pointing to the right. Out to infinity, where it's 0, right? But that's at infinity. The exact same argument applies for the left side. The blue charge will always be a little bit closer. There is not actually any region where the electric field goes to 0. A little bit of a trick question. Right? There's not actually a region where it goes to 0. It's always going to be non-zero except at positive and negative infinity. So for part A, there's no space where the electric field magnitude is 0. Now, let's say the same thing about what's going on with potential. And let me go ahead and get rid of those so that's clean up for later. So I'll go ahead and write out this answer while we're here. Part A, there is no place where the magnitude of the electric field is equal to 0. Okay. What about for the potential? Let's draw it on this side. So if we're thinking about the potential, roughly speaking, remember, it doesn't have a direction quite in the same way anymore. So what I'm going to do is I'm going to kind of graph this out from the very beginning. I'm going to skip almost to part C. If I'm looking at my orange particle, I am expecting to see a potential that is maximized. What's 1 over 0 is infinity. So it's got this 1 over r kind of deal going on like this. Kind of like that. And over on the other side, kind of like that. Right? Where it goes up to infinity right at this point up here. Okay, let me think about the same thing with a blue charge. Well, it's a negative charge, so I'm going to have a negative potential, but it's going to be doing the same thing, right? It's still a 1 over r. So it should look like that, and it should look like that. So let's think about the differences between these two now. If I'm looking for a spot that's actually going to be 0, And I'm still going over a 1 over r kind of deal. Can we all agree on the right side here, while there is a negative and there is a positive in kind of the same way, the orange is always going to be a little bit greater in magnitude than the blue. There's always going to be a positive potential out to the right side. There's always going to be a negative potential out to the left side. But right in the middle, we might actually have a shot. Because it's very, very negative right here, and it's very, very positive right here. And my net potential is going to look something like this. Right here in the middle, in between these two, my potential is 0. Starts from positive, goes down to negative, and the way that I could write that, V net is equal to K Q1, or let's do, how should we do this? We'll do Q positive over, if it's 1 centimeter, it's 0.01, plus K Q negative over 0.01. That spot right in the middle should sum up to be 0. As long as these two charges are equal and opposite, I'm expecting a potential to be 0 right in between them. I am plotting out the magnitude of the potential for all these curves. So this is the potential because of, I'll call this V positive. Call it, please draw. Call that V positive, call this V negative. It's the potential from each charge. So the black line is summing them up together. I know it's a little bit of a busy picture, right? There's a lot of stuff to see on here. So it's a little bit confusing at first, but that's why I recommend drawing this out for yourself, kind of following along how I'm drawing. Go ahead and draw out all these pieces yourself. See how all these pieces would match together. Better yet, if you can, I would highly recommend trying to draw this out, try to plot this out in some program that you've got, whether that's Excel or MATLAB or Python or anything like that. I would recommend trying to plot this out yourself. Sum up these values, sum up, go for all 3 of these plots. Now, on the outsides here, in kind of the same way, it's a little bit more positive. Whoops, that should be in black, please. It'll follow mostly the positive because that's always a little bit greater magnitude. So always going to follow the negative out here because it's a little bit greater magnitude. So that's what I would expect to see. I know it's very busy to see on here, but the black line is my V net. The orange line is my potential from the positive charge. The blue line is my potential from the negative charge. As for my electric field, I'm expecting to see, again, it's going to be dominated by positive out here. It's going to be pointing always to the left in this region, so something like that. And then, again, always pointing to the right. Let's go ahead and write out B. V is equal to 0 at x is equal to 0 centimeters. Now, remember that if you did want to do this algebraically, you could still set this up in the exact same way. So let me do this in I'll do dark green for now. That's a fun color I haven't used in a while. If I wanted to find the V net normally, what I would have to do is I would have to take this same kind of deal, but this would be like 1 over, say, x from here, and then if there's a separation between these two, right, it's something like s minus x at that point, if I wanted to find something like that. Just in case these charges weren't quite the same or something like that, if they weren't centered up, this one we can kind of see it and set it up that way. But you might have problems where it's not such a clear-cut case. You've got to find some way to relate both of those distances to the same x. That's how you treat those other problems. For all of these points, as long as I'm dealing with a point charge, my potential follows this shape, that the potential is equal to kq over r. So the magnitude of each of these is going to be just kind of scaling like I've got here in orange. Right? For the positive charge, it starts very, very positive and gets closer to 0 as I go out from it. For the negative charge, because it's got a negative sign in it, it'll start at the negative infinity and slowly go to 0 as I get farther and farther away. In the middle here, what I've got, because they're going to be equal charges, I'm going to see essentially the same magnitude, but flipped over. When I'm looking at this then, I'm essentially looking for the spot, so I can see it's going to be, very negative out here and very positive over here, but right here in the middle, since I'm the same distance away from each one, I am expecting this one to be 0. Right? And that's exactly what I'm getting here. If it's positive 2 nanocoulombs and negative 2 nanocoulombs, because the distance is the same, I should get a potential of 0 right there. But it's really just stacking these things together. I'm summing up the orange and the blue lines together, and this black line is about what I would expect to get. Right? It's not very accurate because I'm hand drawing this thing, but that's about the shape that I would expect to see because of summing those two lines together. Let's try this thing out. So let's create some x values, for example, and let's say we're going to start from negative 1 centimeter, and then let's go... I'm going to make a really big long list of these things just for fun. So here's all of our x values that we could possibly have, and we'll go all the way out back to 1 centimeter. A little bit farther, there we are. So something like that. Here's our x values, and I know it's a big long line, but let's not worry about it too much quite yet. Then we're going to say, okay, here is my, go ahead and label all these things out. So here is my, call this V negative. It's my potential from the negative charge. I don't necessarily need real value for this. I just want to take the general shape. We could say negative 2 nanocoulombs. Let's just say negative 2. Negative 2 nanocoulombs, and then let's ignore that factor K for now. Divided by... The way that I'm going to take this is that x minus 1 centimeter. That's how we get it, right? So that's what the intercept should be. It should be x minus the intercept. So the intercept is the negative 1. So there's that. And we're going to replace x with b1. And it's mad because we tried to divide by 0, but that's okay. So we've got all these values now. Take our v positive, and it's going to look very similar, right? So I'm going to carry this thing down, but now it's going to be positive 2. This distance, if I was to look at this spot right here, from the blue, this would be, I'm starting at, you've got to think about it like this. R would be my x plus 1. Right? When I would say that my x value is 0, when x value is 0, that puts us right here, 1 centimeter away. So when x is negative 1, we get directly on top of our charge, which is r is equal to 0. So that's what that's going to look like for the blue one. For the orange one, we would see something like this. So we're starting at positive 1. When we plug in x is equal to 0, we should see positive 1. But if x is anything other, so when x is equal to 0.5, for example, our r value should be 0.5. It gets closer as time goes on. If x was negative 0.5 instead, right here, then we would see the r value would be 1.5. That would be the farther away. So that's how we need to have these two set up. For the blue one, it's x plus 1. For the red one, it's plus 1 minus x. And that's what I've got here. So plus 1 minus x, or I guess minus x plus 1. And now we've got these two set up. And the reason I'm doing that is because I'm getting this graph. This is exactly what I was talking about. So let's go ahead and scale this thing up. Yeah. You can kind of see that one, right? Here's how they both decay down. Now I'm going to create one more line, and I'm going to call this one V net. And V net is just going to be, absolutely. I want to finish this thing out just for the fun of it, right? Because we're here at this point. So let's go ahead and do it. And now it's going to be upset because it's got that thing. Something like that. And let's delete this one for now because I want to plot all three of these now. Oh, perfect. And it even did it in gray for me. So we can see it's kind of hard to see, honestly, right? If I'm scaling these, let me see if I can't. I want to see if I could zoom in a little bit more. I guess I could do it manually, but yeah, we can see it. It crosses right at 0. Kind of splits between those two. So this is a little bit of a better way, better than my hand drawings, but that's what we're expecting to see here. But this was good though. I'll include this actually in the video for this one. So thanks for bringing it up. It's, I think, worth doing. I think it's a good thing to look at. We might remember that when we started talking about electric fields, we spent a fair amount of time looking at point charges and special shapes, and then we said, hey, what if it's not a point charge? What if it's not just any sort of single value freehand? What if it's actually a charge distribution, if a three-dimensional object that has charge spread all the way throughout it? We did integrals, right? We basically said, hey, if we need to sum up a bunch of pieces, that's one thing. But if we need to sum up a whole lot of them, we need to use, well, addition through calculus at that point. And don't worry too much. Don't panic quite yet. These integrals are going to be a little bit easier than when we were doing the electric field, right? I promise. Because what doesn't show up anymore in these integrals, r hat's not here anymore, right? Since there's no direction to worry about, we don't have to deal with any r hat direction nonsense. We could just focus on the scalar quantity, and that makes these integrals a lot more bearable to do. But we basically go through the exact same thing as before, right? We're saying, okay, if I wanted to find the potential, I would need to take every piece of the potential, dV, and that's not volume, that's potential. But I would take dV and I could basically say, okay, well, every single charge contributes a little bit of potential as k dq over r. Plug that thing in, and then there's the challenge. We need to figure out how to talk about dq and r, but that falls into a lot of the same steps that we were seeing when we were doing the electric field, right? Same thing as before. So let me do an example with a problem that we're kind of familiar with already, right? The horizontal rod. So it's got a total charge Q, it's got a total length L, and I'm told that I have a point P that is capital R away from the center of the rod. So what would I do? Well, I know that I'm going to find my potential by integrating every point of dV, which means I need to figure out some way to represent lowercase r and some way to represent dq. I have a linear charge density lambda. If I were to take a tiny little piece of the charge dq, as I've got it here on the drawing, then I would say, okay, well, how much charge is on that piece? It would be the charge density times the length of my tiny piece of charge, lambda times dx. How would I talk about my distance away from that? Well, I need to figure out some way to do this. If I have a bunch of x quantities, if I'm going based off of the x-axis, then this point dq would be r minus x away from me, right? And so when I go to the negative values somewhere over in this region, I would have essentially r minus minus x, which would be a greater distance. All that works out. Now, that step right there actually has a few different options. I don't have to go with this. This is not the only possible thing I could put in there. I could set this up where r is just equal to x, but that would change my bounds. There's a few different ways to do all of these integrals. You just have to make sure that your bounds accurately reflect both ends of the rod. So I could change this instead. So what if, for example, let me do this in a different color. Let me do this in this green color here. What if I said r is equal to x instead? Well, then my bounds would be capital R my endpoints would be capital R plus L over 2 all the way to capital R minus L over 2. Does that make sense? How we would get those two bounds? I would just be plugging those in as my bounds for x. So there's a few different ways that we might consider doing that integral, whatever makes the most sense to you, realistically. Right? I might do that in a few different ways. Sometimes, yes, it does seem like the first way with extra steps, but sometimes I like that way a little bit more because I think it's a little bit more intuitive because I'm just looking at the x-axis and where am I going along the x-axis? Here's one point and here's the other point. So sometimes I do it because it's a little bit easier on the integral side of things. Because if we had gone through that instead, we would have just been integrating 1 over x. And that's a little bit more manageable. You know, it's not hugely different. They should all get to the same spot at the very end. But anyways, let's stick with what we've got so far on screen. So we said r is equal to r, capital R, minus x. Then we would just need to do the integral of that. Well, k, lambda, they're both constants. Go ahead and pull them to the outside. The integral of 1 over r minus x is going to be -1 natural log of r minus x. So keep in mind that if I was doing something, let's do this in green again. Integral of 1 over x is equal to natural log of x. If I was to take the integral of -1 over x, this would be negative natural log of x, right? Since there is a negative x on bottom here, that's where this -1 is going to be coming from. It's part of the chain rule for doing that integration. Evaluated from negative L over 2 to positive L over 2. Plug those values in, and then I can take the last step of combining these two. I've got a natural log minus another natural log, so I can combine them into a fraction together. That's one of those fun tricks you can do with natural logs. They've got some special properties that make simplifying them a little bit easier. But technically, the step right before this, you know, the second to last line is still the correct answer. If you plugged in all the stuff right there, you'd still get the right answer. But this is just a little bit more simplified on the bottom. But anyways, one of the things, if you mess up these bounds or something like that, what if you put positive L over 2 to negative L over 2? You get a negative number at the end. And that's probably fine. Let's be honest. If you messed up the bounds a little bit and you got a negative answer from what you should have gotten, but you know it should have been positive, get rid of the negative sign, right? I'm not going to bust you on that one. I mess up my bounds for these things all the time like this. It's not a huge deal, right? What's a negative sign between friends after all? So just keep that in mind. Know what you should be expecting to see here, right? Think about what answer you should be getting by the very end of the problem, and just make sure that the answer that you find agrees with that. And if it doesn't, think about why. Think about if there's an easy fix or what might be causing that. So, got one problem for you guys to try here. Right, and this is another one that we've seen before. We found the electric field for this one, but now we're going to find the potential because of it. So if it's been a little while since you've thought about how to actually integrate this one, you might want to look at old notes to see some of the steps we did, just in case, but try it without first, right? See how much you can remember, go through this thing a little bit, don't immediately jump to those old notes, but, you know, we will cover this in good time anyways. There's a good way to integrate this one, and I'm going to recommend that your variable for integration, it's easiest if you use d theta. But there are other ways if you'd like to use those instead. But anyways, let's go ahead and take a little bit of time working on this one, then we'll come together and take a look at it. Okay, so let's take a look at this one. So there's actually a really fast way to do this. Right off the bat, I could say, hey, every single one of these pieces is, if I look at any piece of Q, let me not do it like that. Let me say, well, let's do dV. Or rather, let's split it into tiny pieces. So let me look at like this piece, for example. If I looked at that piece right there, whatever that charge is, K, Q over R. Let me move over. Let me do that piece. I find again K, Q over R, and K, Q over R, and K, Q over R. My answer is K, Q over R. That's it. Every charge is the same distance away. Since, or every piece of the charge is the same distance away. Since it's capital R the entire way through, and there's no direction to worry about, that's all I would need. But for the sake of it, yeah, there was, but it was for electric field. Let's go ahead and actually go through the integral because it's some good practice still, right? Even if we know what the answer should be at the very end, the whiteboards are here for our practice, so let's take advantage of that. And it's a nice way that we can check our answer at the very end, right? We already know what this should look like, so let's make sure we can actually get there if we were to go through the entire process legitimately. So I'm only given two variables to really work with here. We want everything to be in terms of Q and R by the end. So let's go ahead and start how we always start with these. I want the full potential. To find the full potential, I'm going to need to sum up every single piece of the potential. How do I describe every piece of the potential? Every piece of the potential comes as K piece the charge over R. Plug it in. K dq over little r. Okay. I run into the issue again. I don't know how to integrate over what are the bounds for dq. I don't know. So I need to step away for a minute and remember how I used to talk about a bunch of pieces of dq. Let's highlight one of these regions. I'll do it in green so it's a little bit more visible still. Let's take this piece right here. If I was to talk about this piece of charge, well, I have a one-dimensional rod that's been curved into a semicircle. So what I could say is that maybe this piece has a length ds, then lambda times ds would get me there. Right? That would work. And I would just say, okay, well, lambda is equal to q over, they said it was a length L, but we see from a semicircle, half the circumference, that length L, in terms of r, should actually be 2 pi r times 1/2, right? So just pi times r. That's what we've got. That's my lambda value. Okay, well now I run into a little bit of an issue because what are the bounds for ds? Technically right here, we could use ds for our integration. That's a totally viable thing to do, actually. And the way we would set that, we would just set our bounds for integration would be essentially here's 0, s is equal to 0, all the way to s is equal to pi r. We could use those as our bounds of integration. This is a little bit of a unique problem because if we do it like that, it only really works because lowercase r is actually equal to r here, right? That value never changes, so we don't have to worry about putting things in terms of s like that. Otherwise, if we were at any other point, this would be a little bit nastier, right? But specifically for this problem, there is a way to integrate over ds, but I'm willing to bet that that is not what you thought of at first, and that's not really what I want to stick with. I want to go ahead and think about this in terms of something that we're a little bit more used to integrating over. ds is not the way to go. So let me think about a circle for a second. Let me imagine what I've got with a circle. My full circle, if I wanted to know the length all the way around the circle, the circumference would be equal to 2 pi capital R. What if I didn't want the entire thing? What if I only wanted a piece of it? Well, what I'm really doing there is I'm saying that a length, s, is equal to however much of an angle I take around the circle times that radius. So if I was only interested in this portion right here, I would simply take that slice, delta theta, multiply it by the radius, and that would be the distance s. Try and make that a little, I made it even messier. Oh no. Make it a little bit more clear, something like that. It should look cleaner, but we know what I'm going for. I would take that angle delta theta, and then however large delta theta would be, the max it could be is 2 pi, but once I hit 2 pi, I'm back to the circumference of a circle. So that's what agrees, right? So if I was to take a tiny piece of my length, let's shrink s down to as small as it could possibly be. ds. Theta becomes as small as it could possibly be. d theta. r is still r. So that's how I'm going to transform ds. So dq might be lambda times ds, but ds is equal to r d theta. Now, do I know how to integrate over d theta? Yes, I do. And there are actually a couple different ways that I might do this. So right off the bat, what I could consider is my angle right here. This is where theta is equal to pi over 2. Down here, this is where theta is equal to 3 pi over 2. One of the fun things about this problem, again, because direction does not matter, if I spun this thing by 90 degrees, I could do 0 to pi, and it actually wouldn't be any different. If we had r hat, we would need to change how r hat was if we wanted to try and rotate this thing around. But because we don't have to deal with direction, anything goes. Really, the most important thing is the difference between these two bounds has to be pi. As long as your difference between these two bounds is pi, you'll get the right value. But anyways, let's just go ahead and stick with this one for now, because we've already got it written down. So if we do something like that, then we're going to say, okay, well now dq is equal to lambda capital R d theta, and we also know that r is equal to capital R, because it's not a changing radius. K lambda r d theta over capital R. I'm going from pi over 2 to 3 pi over 2. Sorry if that's kind of small for anybody. I can pull out my constants and I can cancel out that r, right? R over r is just 1. Get rid of that thing. K lambda integral of d theta. What's the integral of d theta? Well, it's just theta. 3 pi over 2 minus pi over 2 is just pi. K lambda pi. My last step, I need to plug back in for lambda, right? So we said lambda at the very beginning was q over pi r. So V is equal to k q pi over pi r. Pi's cancel out. K q over capital R. There we are. That's it. I love some of the problems like this, and I know I keep saying that, but I love some of the problems like this because there's, like, realistically multiple ways to approach this. It requires a little bit of creativity. Some of the older problems we did, there was really one way to get there, right? Sometimes we run into that. There's only really one real method to get to the final answer, but for something like this, we've got a lot of freedom. As soon as an integral gets involved, there's oftentimes a lot of freedom with how you want to pick things and how you want to describe things. But what's most important then is being able to describe what you're doing with that integral, right? If you're just kind of following the steps because you've seen me do it before, you're going to have a little bit of a rough time, to be honest. You need to be able to talk yourself through these decisions that we're making in the integral. Why are we making the decisions like this? Could we do it another way? And if you're a little bit unsure on how to handle these integrals right now, I would heavily recommend trying it another way. So I would recommend, though, like if you're not entirely sure what you're doing with some of these integrals, go ahead and try to mix up some of the things. When I'm talking about like changing the bounds of the integral, try it, right? See if you can figure out some different bounds for the integral and describe why you can use those bounds or how you're using those bounds. And does it get you to the same place, right? Think about those things. Consider all those details. Can you integrate with your variable being ds? Does that still work? And yes, I already kind of told you it can, but I want you to talk about why. It's just a good way to practice some of these things. And if you're starting to feel a little bit more confident on the integrals now, you might consider actually going back to our electric field integrals and trying some of those again. And seeing if you've got a greater understanding of those things now that you've been through them a time or two, and now that you can kind of see that we can really mess around with a lot of these values. As long as you can describe what you're doing, that's the most important step. So, I think that is the end of our 25-2 lecture. There is a lab to go along with this. I sent out an announcement just a little while ago because it wasn't on the calendar, but it is now. It's a fun little lab where you get to play with those equal potential lines. You get to see some cool things. When you turn on the voltage setting in the VET lab, it looks a little bit like a rave might, right, with those glowing red and blue lights. So there's a lot of fun things to do in this one, though. And you can kind of see some of the things. You can use this as a way to check. I had this set up in such a way that you can find, yes, there is a spot right in between these two charges where the potential is 0. But if you look on the graph, there's no electric field is equal to 0. So some cool things in here. It's a lot of fun to play around with. But, yeah, that'll be it.